I'm going to give you a hint with this problem before we even work through it. You don't need an ice table with this problem. But if we go through and we treat this problem the same way we've treated every other problem, hopefully we'll realize that we don't need to do that. So this is a first of our problems where we're actually going to not be calculating an equilibrium constant. We're going to be determining equilibrium concentrations. So this problem tells us, in a study of the conversion of methane to other fuels, a chemical engineer mixes gaseous methane and water in a 0.32 liter flask at 1200 K. At equilibrium, the flask contains 0.26 moles of CO, 0.091 moles of H2, and 0.041 moles of CH4. What is the water concentration at equilibrium? They give us Kc for this process at 1200 K of 0.26. So again, if you're not exactly certain how to start these problems, keep those steps in your mind and work through those steps. You will get partial credit for each of those steps that correctly moves you in the right direction. First step, write a chemical equation. So for this process, the chemical equation is CH4 gas reacting with H2O gas, and because they tell us it's at 1200 degrees or 1200 Kelvin, that's a good indication that this is going to be gaseous water, which means it is going to become part of our equilibrium expression. If it was liquid water, it would not. We react to form carbon monoxide gas and H2 gas. Remember, we always need to make sure that we're balancing our chemical equation here. My carbon atoms are balanced, my oxygen atoms are balanced, but I can see that I have 6 hydrogens over here and only 2 over here. This one balances fairly easy by just putting a 3 in front of our hydrogen. First step, write chemical equation. Second step is write your equilibrium expression. Write your reaction quotient. So QC here, since we're given moles, we know that we're not dealing with partial pressures, so we want QC, plus they give us KC for this. QC equals the concentration of H2 cubed times the concentration of CO times the concentration of H2O times the concentration of CH4. First step equation, second step reaction quotient. Third step is to make sure that we have the concentrations of species in the units that we need. If we're dealing with Kc and Qc, that means we need concentrations in units of molarity. We're given numbers of moles in a certain size flask. So from that, we can calculate concentrations. So they tell us that we've got 0.26 moles of CO, and importantly, they tell us, this is a huge thing, I should highlight this with a highlighter, at equilibrium. So that means the CO concentration is an equilibrium concentration, and it's 0.26 moles in 0.32 liters, and so the equilibrium concentration here is going to be 0.81 molar. The concentration of H2 at equilibrium. H2 at equilibrium is 0.091 moles in the same flask, so it's 0.32 liters, 0.28 molar. And lastly, they give us the concentration of CH4 at equilibrium. That's equal to 0.041 moles, 0.32 liters. That's equal to 0.13 molar. First step equation, second step reaction quotient, third step make sure that everything's in your right units. All right, this problem is asking us to solve for Kc. So Kc equals the equilibrium concentration of H2 cubed. Oops, I'm sorry, this problem is determining equilibrium concentration. Equilibrium concentration cubed times the equilibrium concentration of CO over the equilibrium concentration of water times the equilibrium concentration of methane. And they tell us for this problem that it's equal to 0.26. Okay, well, they gave us this, they gave us this, they gave us this. This is what we want to solve for. We don't even need an ice table. This is just a simple algebra problem. So I left this space intentionally blank because that's where you would put an ice table but you don't need one for this problem. All we need to do is put in the pieces of information that we know and mathematically solve for the piece that we don't know. So our equilibrium concentration of water is equal to 0.53 molar. Most times you're going to need an ice table, but again, we've seen a couple of times where you don't. So set it up. If we wanted to figure out what the equilibrium concentrations were, we would still need to do this expression, right? But often we're going to need to use an ice table with variables to put information in here. We didn't need to do that. There was only one variable that we had here.